Today, and good morning, today, is Henry Wilton, and he'll tell us about the surface of groups of abstract tree groups.
Good morning, everyone. Is this working? Yeah, good. Okay, thanks. So for people who are visiting here, quite often, kindly say how much they're enjoying visiting Cambridge. Since I live here, I'm not going to say that. Instead, I want to say how fantastic it's been during this conference and the workshop to have so many interesting and nice people visiting here for such a long time. It's great. It means I get to see you all without having to go anywhere, which is, fantastic. Okay, so, right. Okay, so, let me also say, so this talk will be pretty similar to a talk I gave at YGGT in Oxford a few months ago, so if you were there, apologies. Okay. So I want to simplify my life slightly by making an edict at the beginning of the talk, which is that all infinite groups are torsion-free, okay? Unless I say otherwise, all right? It's not an important thing, but it just means that it just makes various statements that I make slightly easier to make. Okay. Right. Okay. So, today I want to talk about a question that is probably pretty well known to this audience. It's a famous question in geometric group theory, and it's usually attributed to Gromov. What he basically wants to say is, the question is something like, if gamma is hyperbolic, well, gamma is a group, of course, must gamma contain a surface subgroup? So what do we mean? What do we mean by these words? Well, all right. Well, of course, a surface subgroup is, well, a surface group is the fundamental group of, we'll say, a closed surface, right? Not the sphere. That's not allowed. That's cheating. All right, so a closed hyperbolic surface, let's say. So in other words, must there exist pi 1 sigma, a subgroup of gamma, where sigma is a closed hyperbolic surface? Okay. And of course, this question is famously motivated by the three-manifold setting, right, in which you're looking at a hyperbolic three-manifold, and you dearly love to know that there's an immersed three-manifold, immersed surface in there, and you dearly love it. You'd like it even better if it were embedded, and then you could cut along it and play fun topological games. And so, of course, in classic geometric group theory style, when one believes something about a hyperbolic manifold, you think, well, maybe it's true for all hyperbolic groups. This is a standard way of generating questions in geometric group theory. Okay. All right. And of course, you look at the question like this, and of course, the first thing you say is, well, no. I can come up with a counterexample very easily, right? Okay. There's an obvious counterexample, right? Okay. Well, okay, it could be the trivial group, but let's come up with a non-trivial counterexample. Of course, it could be a free group, right? Free groups, famously, every finitely generated subgroup is going to be free, and therefore you're not going to have a closed surface subgroup, right? Okay. Okay. So you need to put some adjective in to hypothesize that away. And so what you normally, so the easy thing to say is you say gamma should be one-ended and hyperbolic. Okay? So, of course, one-ended just means, by Stalling's theorem, that, well, it just means that the group doesn't split over a finite subgroup. In particular, it doesn't split over the trivial group. In the language that we were just hearing about boundaries, it just means that the boundary is connected. Okay, so it's a very natural hypothesis, and once you put that in, all of a sudden you have an interesting question. Right? So Gromov asked this question. Well, I think this question was certainly around in the 80s, and probably until about 10 years ago, we knew next to nothing about it. I would say, or something very, very close to next to nothing. Okay. Yeah, okay. I think it's worth, before going on, it's worth spending a little bit of time asking ourselves whether, whether the motivation for this question, what really is the motivation for this question, and whether it's good motivation. I said, well, we can generate questions by asking questions about hyperbolic manifolds and then transferring them to hyperbolic groups. Well, that's an okay way of generating questions, but sometimes those questions are kind of random, because then they won't, even if you know the answer, you don't necessarily get sort of a good application, okay? Because maybe surfaces in manifolds surfaces in three manifolds are also codimension 1 things, right? That's not going to be true here, right? So actually, that's not going to be true for general hyperbolic groups. So somehow, the motivation should be a bit different. Here's another way of motivating the question that I'd like to mention. So I won't write this on the board because I want to. I'm conscious of the time, but so suppose generally we do want to be able to construct subgroups of groups that we're interested in. That's quite an important problem, an important thing we need to be able to do. And in hyperbolic groups, there's a kind of subgroup that we're really good at constructing. Namely, we're really good at constructing free groups, right? And the reason, or free subgroups, and the reason we're good at constructing them is because of the ping-pong lemma, right? The ping-pong lemma says that if I find one element that sort of moves things over here, and I find another element that sort of moves things over here, then together they're going to generate a free group, basically. That's great, okay? So free groups are everywhere. There are zillions of free groups in hyperbolic groups. It's a technical term. On the other hand, there's an amazing theorem which one should probably attribute to some combination of Thurston, Gromov, Celan, Delzant. So it's certainly the best version, the best and final version of the theorem is due to Delzant, which says that if you look at a one-ended group and you try to find, if instead of looking for free subgroups, you look for one-ended subgroups, right? Then for any h that you're going to try to find as a subgroup, there are at most finitely many conjugacy classes in gamma that are isomorphic to h. Okay. Right. So that's totally non-true in the free world, but for one-ended subgroups, there are only finitely many conjugacy classes of each type. All right. So that shows that constructing one-ended subgroups is going to be much, 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 much harder than constructing free subgroups. Okay. And that already makes you think, well, okay, ping-pong's wonderful, and we use it for lots of things, but what else can we do? Can we do anything else? Can we develop more refined techniques? Okay, and so because of that, I think it's worth, and I think Gromov probably would have might well have said something like this as well at some point. I think it's worth relaxing this a little bit to just ask yourself a sort of relaxed version of the question, which is still very interesting, I think. So if gamma is hyperbolic, must gamma contain, let's say, a one-ended, let me try and say this properly. A one-ended subgroup of infinite index. Okay? And again, so in other words, this is asking, can I find an interesting one-ended subgroup, right? Now, of course, if gamma itself were one-ended, then of course gamma would qualify, and we don't want that. So that's why I put in this infinite index hypothesis. So now again, you stare at this question, and again you think, well, no, right? I can come up with a counterexample easily. Even if gamma is one-ended, there's an obvious counterexample to this. Thank you. Very good. Surface groups, right? Okay. So again, rather like in this case, you have to hypothesize away a few bad examples, right? So we want to say gamma is hyperbolic, one-ended, and not a surface group. Must gamma contain a one-ended subgroup of infinite index. And so this is still a really interesting question, and I think, arguably, approximately as interesting as that one. Somehow, one way of motivating question 1 is it's just an instance of question 2 where we just agree that surface groups are somehow our favorite one-ended groups, right, or the ones that we sort of find, that we believe we're going to be able to say the most about. Okay. And in fact, I'm not going to write it on the board, but there's even a version of this question that makes sense not for hyperbolic groups, but for arbitrary finitely presented groups, pretty much, right? So I think you can ask yourself, I think the following is still open. if you've got a one-ended, finitely presented group, must it contain either a surface subgroup or a Baum-Slag-Solitar subgroup? Right. As far as I know, that question is open. It seems insane that there's a question that could be open about arbitrary one-ended, finitely presented groups, but I think that question is open. And I think it's particularly interesting in the amenable case, right? So the question there is one-ended amenable group, finitely presented, must it contain a Baum-Slag-Solitar subgroup? Right? Sorry, that's not open?
Well, there is this H&N extension of the rigidity group, which is finitely presented.
Yeah.
And then it's torsion by cyclic. So it cannot contain surface or bounds.
Fantastic, I learned something today. Thank you. Okay, good. I'm glad I didn't write that question on the board. Sorry? Sorry?
All groups are true.
Well, it's... well, yeah. Thank you, Ian. Yes, okay. That is very interesting. A torsion-free example would be even better, but that is good. I didn't know that, so that's great. Okay.
Can you repeat that example so everybody can...
Well, apparently there's an H&N extension of the Gromov group, which is finitely presented, and you're saying every infinite index subgroup is going to be cyclic by...
Well, the Gromov group itself is torsion.
Well, oh yeah, so everything's going to be cyclic by torsion, yeah.
The ascending H&N extension is going to be torsion by cyclic, and therefore it cannot contain Baum-Slag-Solitar or surface groups.
Okay, there we go. Excellent. All right, good. Fantastic. Progress. Okay, that's good. Now, all right, so let me, I'm not going to write it on the board, but let me now mention some famous history of these questions. So, question one, as I say, until about 10 years ago, we knew almost nothing. Then there was this spectacular progress by Kahn and Markovich, who answered it in the case in which people really cared about, namely the case of hyperbolic three manifolds. Right? So closed hyperbolic three manifolds contain surface subgroups. Kahn and Markovich proved that. That was great. And then not too long afterwards, there was also a really fantastic development by Caligari and Walker, who answered question one positively for random groups. Right. So I'm not going to give the definition of random groups because I would like to have time to do something else today. But roughly speaking, you take some generators and then you pick some relators at random, and when the relators get very long, then then your group is very likely to be hyperbolic, and it turns out it's also very likely to contain a surface subgroup. So that was really fantastic progress. Both of those really gave strong evidence that question one might well have a positive answer, or at least has a positive answer in lots of interesting cases. All right, but today I want to talk about a much more straightforward family of examples. Okay, so today we're going to talk about this kind of example. Okay, so take a free group. Okay, so let the finitely generated free group, let F be a finitely generated free group, and let's take W to be a word in the free group. Okay, well then I can now build a hyperbolic group in a very naive way, right? Or at least a group that's frequently going to turn out to be hyperbolic. I'm going to let D of W be the double of F along W, right? So it's just going to be F amalgamated with F along the cyclic subgroup W, okay? And almost always we're going to want to think of this via a topological picture. So we'll think of our free group as the fundamental group of some graph. We're taking two copies of that graph. We're taking a cylinder that we're going to put between them, and then we're using W as an attaching map to attach the ends of the cylinder to the two copies of the graph. Okay? And I think this graph will usually be called X. Okay. All right, so this is somehow a very, very naive family of examples, right? And more generally, you might want to take other free groups and other cylinders and come up with a graph of free groups along cyclic edge groups, right? But somehow thinking about this family of examples will be quite enough for us today. Okay. Okay. So I said we were going to be able to generate families of examples that we should be interested in this way. So we're interested in groups if they're hyperbolic and one-ended. All right. So when's this going to happen? So hyperbolicity is quite easy to characterize using a famous theorem of Best, Wiener, and Fein, their combination theorem. Okay, they showed that. What did they show? Well, they showed that if you glue two hyperbolic groups together along quasi-convex malnormal subgroups, then don't worry what malnormal means yet. I'll tell you in a second. Then you get something that's hyperbolic. All right. So in this case, that translates just into the condition that W shouldn't be a proper power. Okay. So if W isn't V squared or V cubed or V to the 4, for example, then they showed that D of W is going to be hyperbolic. And actually the converse is true, and that's quite easy to see. If W is a proper power, you can go away and look for a Z squared in that group, and you will eventually find it. All right, if you're looking sensibly. So, okay, so Best, Wiener, and Fein showed that D of W is hyperbolic if and only if W is not a proper power. Okay. And then, right, so what about, the other condition we want is one-endedness, right? Okay. So, for instance, we're worried that this double we're looking at might be still a free group, right? Think about it, that can really happen, right? So, for example, if you choose W to be a basis element of F, if you choose it to be a primitive word in F, then that double's still a free group, okay? And more generally, if you can see that if W is contained in some proper free factor of F, then the double will still split freely, right? Because you'll be able to just sort of move, factor out that free factor still on either side. So we can see that if we want this thing to be one-ended, we need to assume that W isn't contained in a proper free factor of F. And it turns out that that's an if and only if. That's a lemma that's usually called Schenitzer's lemma. Although somehow there have been lots of improved versions of it since Schenitzer first proved it in the 50s. But the basic point is that D of W is one-ended if and only if W is not contained in a proper free factor of F, okay? Okay, so, but, if you've thought at all about words in free groups, you should know that both of these conditions somehow are completely generic, right? If you pick a word at random, you will certainly get a word that satisfies both of those things. Those are both very rare things to happen, right? Okay. And because of that, so this is still generating absolutely loads of examples, right? And so one wants to answer Gromov's question for it. Okay. And somehow, although they're very naive examples, there's something a little tricky about them, because unlike in the famous Kahn and Markovich or Caligari and Walker instances, there they were dealing with hyperbolic groups that were guaranteed not to be free, right? And guaranteed not to split free, right? So they could go out and look for surface subgroups and find them all the time, right? Okay. Whereas here, you've got a group that's hyperbolic and that might be free or might not be free, right? And recognizing whether or not it's free is the same as recognizing whether or not W is a primitive element of F, right? And if you've thought about that problem at all, it's a reasonably tricky problem, right? It was solved by Whitehead in the 50s, but it involves Whitehead's algorithm, which is related to the Whitehead graphs that Yao was talking about in the last talk. And it's a non-trivial problem, and you have to somehow build that into the proof, right? Because otherwise you're going to prove that all of these guys contain surface subgroups, and then you prove that all free groups contain surface subgroups, and then you know you made a mistake, right? Okay. So it's a very basic but sort of interesting class. Okay. Right. Yeah. So let me give some history. So I think actually a lot of people who I'm mentioning today are in the audience, which is nice. So let me give some quick history of just thinking about these examples. So right, so Caligari managed to find surface subgroups. So he managed to deal with he managed to find surface subgroups in the case where he already had some homology some second homology to begin with, right? So in other words, in the case where you've kind of already got some sort of homological surface lurking, right? Okay, so Caligari found surface subgroups when H2 of the double, let's say with rational coefficients, is non-zero. Okay? So you can, so then you think to yourself, well, every time I have a condition on the double, I need to translate it into a condition on the word to understand how common this condition is. Right? And you can do that. It's not very hard. You just use the Maya-Vietoris sequence for this picture. And what you see is that this happens if and only if the word W is in the commutator subgroup of the free group. Right? Okay. This happens if and only if W is in the... So again, this is a large class of examples, but it's very, very, very far from generic. It's the opposite of generic. It's, most words will not satisfy that property. All right? And so, and so we see that somehow we sort of found some surface subgroups, but there's still most of the class of examples left. All right. And in some sense, you can sort of think to yourself, well, we already had a homological surface, so maybe you can think of this as like, so in the three-manifold world, you have Dane's lemma, right, which tells you that if you've got this condition, then you automatically have a nice incompressible surface, right? But we're not dealing with three manifolds here. Dane's lemma doesn't work, and so it requires a really interesting and non-trivial argument to get this far. But you can think of it as an analog of Dane's lemma. I guess Dane's lemma is also an interesting and non-trivial theorem. Anyway, right. Okay. So then, after that, it sort of became interesting to try to find examples, show that, to find examples when there wasn't this homology, which you sort of, because you want to sort of see whether, you want to see whether you can still find surfaces even when there isn't homology. And we found, and so in joint work with Cameron Gordon and with Sam Kim, we found infinite families of examples by various techniques of examples for which H2 was 0, but we could still find surface subgroups. Okay. Right, and then really the sort of next sort of really interesting positive progress was made by Kim and Oom, who resolved this problem entirely as long as the rank of the free group was 2. So they were able to answer the question completely when the rank of the free group was 2. But unfortunately, essentially what they did was, they were able to reduce it to a certain number of cases, and of course, which they were then able to check by hand, but, the number of cases were going to get a lot bigger in higher ranks, so it's not quite clear it wasn't quite clear how to proceed from that. All right. And then, lastly, I also just want to mention another part of the prehistory of this problem is that I actually answered this problem affirmatively without any hypotheses on the rank, but I didn't answer question 1, I only answered question 2. All right. So what I was able to show was that, this was in about 2010, all of that stuff was earlier, was that question 2 is answered affirmatively. The doubles. Okay. All right. And indeed, more generally, for graphs of free groups with cyclic edge groups, so for a much bigger class. Okay. Okay. And I want to point out that somehow that there's a relationship between question 2 and question 1, which kind of goes this way, where question 2 actually tells you something about question 1, right? So imagine you're trying to answer question 1, you're trying to find a surface, right? Okay. And suppose you sort of know the answer to question 2, right? So question 2 tells you, well, it gives you a criterion which will be satisfied by any group which isn't a surface group, right? Any one-ended group which isn't a surface group. Namely, if you're not a surface, then you can find an infinite index subgroup that's still one-ended. So that tells you, that sort of suggests, question 2 suggests that there's something extremal about surfaces, right? There's something, that surfaces are somehow some limiting case, right? Where they sort of can always be, anything that's not a surface can somehow always be simplified in some way, whereas once you reach the surface point, you can't go any further, right? Okay, that's the kind of, that suggests that kind of philosophy. Question 2 suggests that kind of philosophy in trying to approach question 1. Okay. Okay, so the, the main theorem today is that you can give up and do something else, because question 1 is true for this class of examples, right? So it has an affirmative answer. So the theorem, I'm going to adopt this practice people have been using of putting theorems they don't want to have to erase on the board. So on this board over here. So the theorem says if gamma is d of w, or more generally any one-ended graph of any graph of free groups with cyclic edge groups, then and gamma is hyperbolic and one-ended, then gamma contains a surface subgroup. Okay. All right, so any questions? That's the sort of meant to be the motivation and the history and the statement. Everything clear? All right. And we will go on. All right, so in what remains of my time, I would like to do 2 things, and will therefore probably fail. I would like to tell you a few consequences of this, because somehow there are a few different ways that you can think of this theorem. You don't just have to think of it as a theorem about checking, about answering Gromov's question in a very specific class of examples. It actually has some wider consequences that I'd like to mention. And I'd also like to say a little bit about the proof. And yeah, I'll do my best. Okay. All right. Okay. So the first thing that the first consequence I'd like to point out is that, as I said, this isn't just a theorem about a very specific class of examples, which is what it looks like. It actually has some consequences for the whole, for the general question, for Gromov's question, for the approach to Gromov's question for arbitrary hyperbolic groups. Here's why. So there's a very nice theorem of Lauder and Tuiken, which what I'm going to state is actually a consequence of their theorem. So this is let me cover. So this is a consequence of the strong accessibility theorem, which Lauder and Tuiken proved. There's also an earlier work on the subject by Delzon and Portugallo. Okay, right. Anyway, but the consequence of the upshot of all this is that if gamma is a one-ended hyperbolic group, then, gamma contains a quasi-convex subgroup H, such that H is one of the following 2 things. Okay. So the first thing it might be is it might be rigid. What I mean by rigid is that you can't split it either over a finite subgroup or over a virtually cyclic subgroup. So you can characterize this very nicely in terms of the boundaries we were hearing in the last talk. It means that the boundary is connected with no local cut points. Okay? So rigid, i.e. the boundary of H is connected without local cut points. Or the other possibility is that H satisfies the hypotheses of the main theorem, of that theorem over there. Okay, so H isn't going to be a double, but it is going to be one of these graphs of free groups with cyclic edge groups. Okay, all right. And so this means that if you want to try to attack Gromov's question in general, you now get to reduce to this case. Okay, all right. Which there's some reason to think is some progress, because somehow local cut points in the boundary are quite bad for these sorts of problems. They tend to introduce difficulties. Okay, so yeah, okay. So the conclusion is that for Gromov's question, we can reduce to the rigid case. Okay, so that was one of the consequences I wanted to mention. The other consequence I'd like to briefly say something about gives you a sort of, well, it involves sort of turning this whole question on its head, right? So usually, if you think of this as work about finding surface subgroups, then the theorem says if you're not free, then you have a surface subgroup, right? Okay. And in fact, it follows from that in this setting, it actually follows from that if you're not free, you can pass to a finite index subgroup and put yourself in the setting of Caligari's theorem. In other words, you can pass to a finite. Ooh, something bad happened. I will ignore it. In other words, there's a virtual Betti number theorem for these groups, right? So more than just surface subgroups, you actually get a virtually positive second Betti number theorem. That's what follows from that. Okay. So not free implies virtually positive second Betti number. You can turn that around, right? And you can say virtually zero second Betti number implies free, right? Okay. So what's that telling us? That's telling us that in this setting we can recognize free groups by looking at the homology of their finite covers. All right. Now, when you trace through the machinery of all these doubles and so on, that comes back to telling us that we can recognize whether this word W that we were talking about was a basis element of the free group by looking at the homology of finite covers. Right? Okay. So I told you that Whitehead in the 50s gave an algorithm that recognizes whether or not a word is a generator of a free group, whether or not a word is primitive, and his algorithm is quite complicated. Well, this gives a procedure that in some sense is accessible to undergraduates, right? Because it's telling you that finite groups and linear algebra are enough to recognize, some would call that representation theory, I guess, whatever, are enough to recognize primitive elements of free groups. Okay, so another corollary that one can state is that right. Is that, how do I want to say this? Well, yeah, no, actually, I don't want to say it as a corollary. I want to say it as a moral. Okay. I mean, there are precise statements you can make, but I don't want to waste the time by going into all the details of making them. But the key point is that finite covers and linear algebra suffice to recognize primitive elements of free groups. Right? So that, to me, actually suggests a kind of fairly profound connection between. So if you're recognizing all primitive elements of free groups, you've got to be saying something about the outer automorphism groups of those free groups, because primitive elements are an orbit of the outer automorphism group. And so there's some, that to me suggests that there's a sort of connection between representation theory and outer automorphism groups that hasn't been fully explored, that one could open up with this. Okay, but that's something for the future. Okay, all right. And another sort of, a more concrete statement that you can make in the same lines is that, well, finite covers and linear algebra, right? So these are, in other words, that's sort of telling you can recognize things by mapping to virtually abelian groups, and virtually abelian groups are residually finite, so you can actually recognize things by just mapping to finite groups. In other words, you get some of the sort of profinite rigidity theorems that people like me sometimes try to prove at the moment. So another corollary of this is that if L is a finitely generated, fully residually free group, and the profinite completion of L is isomorphic to the profinite completion of a free group, that just means all the same. The L has all the same finite quotients as a free group. That's all it means. It doesn't. You don't need to know what the fancy words mean. It just means all the finite quotients of this guy are the same as all the finite quotients of this guy, up to isomorphism. Then, in fact, L had to be isomorphic to F. Okay. So, in other words, right. I didn't tell you what a fully residually free group was. It's some very strong condition on the group, which means it tends to look a lot like free groups, right? So actually, there are lots of settings in which these groups are the hardest groups to tell from free groups. So you can go away and look up the definition later, but the key point is somehow this is telling you can distinguish free groups amongst a class that's very hard to distinguish free groups in. So I think that's sort of I think that's also interesting. And I would love to spend more time telling you about it, but I'm going to try to spend the last 15 minutes or so saying a few words about the proof, because I think there are some ideas in the proof that I'd like to talk about a little bit. Okay. Any questions while I find my place in my notes? No? All right. Okay. No. No. Let's have this picture again. So suppose we want to find a surface subgroup of this guy, right? So we're trying to find a surface subgroup in one of these guys, right? So what would it look like? Well, you'd have to have some surface that was mapping in an interesting way, right? And if you found this surface, then a very natural, well, if you're looking for this surface, then a very natural, well, no, let me start again. If you found this surface, then of course what you'd want to do is make this map nice with respect to this graph of spaces structure. So you'd want to make sure that it was transverse to the central circle here, right? So we've got a little nice central circle here, and you'd want to make this map transverse, right? And then what you'd do is you'd pull back the preimage of that central circle, and you'll find when you do that you get a bunch of essential curves here. Let me make sure I do this right. Something like that, maybe. Okay. Well, maybe. Let's have a bit more fun. Maybe it's like that. Anyway. Okay. All right. And now, of course, what you see is that what happens when you read, right, so what is this telling us about the surface? All the complementary components of these essential curves just go to the free group part, right? That's okay, because they're surfaces with boundary. Their fundamental groups can embed in free groups, okay? But what happens when I read round these red curves, right? What I see is that I find this is going to have to read some power of w, right? I'll get w to the n1, w to the n2, w to the n3, and so on, okay? And so, if I found this picture, what I could do is I could erase everything except for one of these pieces. And what I've got is I've got a surface with boundary mapping to a free group or to a graph in a way so that the boundary has gone to powers of, well, more precisely to conjugates of powers of my favorite word, of the one that I chose. All right? And then you think to yourself, well, what about, actually, that's the whole problem, right? Pretty much. Certainly in the case of these doubles, right? If I found a nice enough map from this surface from a surface like this to the graph, with the boundaries going to powers of w, then I could just take 2 copies of that and glue them together, and with good luck and a fair wind, as Alan Reed likes to say, I'll have found myself a pi1 embedded surface, right? Okay. So strictly speaking, you have to check that it's injective and also that it's something called boundary incompressible. Okay. But we don't need to talk too much about it. Okay. Okay. So somehow so the whole problem isn't really a problem about these particular spaces. It's really just a problem about free groups with your favorite word, right? Or it's a problem about, or if you prefer, it's a problem about graphs with some chosen cycles. Okay. Okay. And so that's the theorem that actually gets proved. Right. So the theorem that actually gets proved is that if x w is one of these pairs, so you get a graph and you get a cycle, or more generally a set of cycles, okay? So I'm going to just call that I'll call that a pair for now, right? Say something pair. Right. Then there exists a something map from a surface with boundary to the graph equipped with this words, right? So a map of pairs, by which I mean the surface goes to the graph and the boundary of the surface goes to the cycles that we've chosen, all right? To the cycles that we need to, okay? Right, so that's the kind of theorem that we need to prove. And as with all the other theorems that I stated, you stare at it, you look at it, and you say, well, this can't be true because I need to add some hypotheses for all the usual reasons. Because if W is a primitive element of the fundamental group of this guy, I can't possibly find an interesting surface. Okay. So we want, let's see. So the surface, we need to make sure the map is interesting, and so we're going to call it essential. So that's just going to mean essential. I'm going to say that means pi1 injective. It means something slightly stronger than pi1 injective, actually. It's also, there's a boundary incompressibility hypothesis you have to put in. But pi1, you can think about pi1 injective, and that's fine. And then we're also going to say that it's admissible, right? And admissible here means, well, okay, let me tell you something else, right? Let's see. When I have this map, in order to explain what admissible means, I need to tell you something else about this picture. When I have this map, what we see is that each of these boundary cycles wraps around W with some degree, right? And it's very natural to sum those degrees up, okay? To try to, and to ask yourself about the total degree, right? So if this surface is sigma boundary sigma, then I'm going to say that n of boundary sigma is the sum of the ni's, okay? Okay, so it's the sum of the total degrees, all right? And I'm doing that in an unoriented way. That's an important technical point which will only matter to the experts, but it's an unoriented way, okay? Now in this case, so admissible is a condition on these total degrees. It doesn't tell you, in this case, when you've only got one loop W here, it doesn't tell you anything actually. When you've got multiple loops W, they could all be covered different amounts, and that would be bad. Admissible insists that they're all covered exactly the same amount. So this n number makes sense even when W consists of multiple cycles. Right. Okay, that's what admissible means. Okay. Okay, so again, we stare at the theorem, and it still can't be true because we need to make sure that this W isn't just a basis element of a free group. Yeah. So I'm going to use the word irreducible. All right. Maybe I should call it fully irreducible. It means roughly the same thing in this case. It means that these w's cannot be separated into free factors of the fundamental group of this guy. In other words, you can't, up to homotopy, have a picture that looks like this. You've got an A over here and a B over here, and W, say W all on one side. Okay, something like that. So in other words, this irreducible hypothesis just means we don't allow that picture. Okay? And that's what rules out free groups and things like that. Okay? Okay. Do I have 2 minutes, or do I have more than 2 minutes? Okay, right. Well, okay. So this is the main theorem that gets proved. Are there any questions about that? Is that right? Now I'm now going to. I'll say I've got 5 minutes, since I told I have a little bit more than 2 minutes, and I'm going to try to very quickly describe the strategy for proving this theorem. And I'm happy to talk about it more later. Okay. So let's see. Yeah. Okay. So what's the strategy? Okay, right. Well, yes, I'll give us some steps. So step 1, we want to study all of these. Right, we're looking for one of these essential admissible surfaces. What we're going to do is we're going to study all essential admissible maps of irreducible things into here, right? Where the things in question are graphs with cycles attached to them. Okay? So study all essential admissible, they're finite graphs, let me clarify that point. All essential admissible maps of irreducible pairs from y, u to x, w. Okay? Okay, we can say I'm going to do that, but how am I actually going to do that, right? Step 2 is we're going to arrange these into some object which reveals some more structure. What we're going to do is we're going to define a cone in a certain vector space, in a certain real vector space, R to the n. In fact, it's going to be the positive orthant of a certain real vector space. Okay. And I'll call this cone C. Okay. And this is a cone that's just cut out by linear equations with integer coefficients. Right? Okay, so it's a very nice cone. And it has the property that integer points correspond to pairs y, u as above, right? So somehow we can arrange all these guys into the integer points of a nice cone, right? The basic idea is these guys are built out of pieces that come from here. The pieces are actually subgraphs of Whitehead graphs, which are not quite the Whitehead graphs that Jarl was describing earlier, but they're very similar. And that gives you a finite collection of pieces. And to describe these things, you have to count how many you used when you built it. And that's what these coordinates are. They're the number of pieces you use. Okay? So people keep pointing out to me this is a bit like normal surface theory. So if you're a three-manifolds person who likes normal surface theory, it's a little bit like that. Okay. All right, and then step 3 is you define a map rho from the cone to R, right? And the map, well, it's harder to say what it does on a particular vector. We haven't got enough notation to say what it is, but I can tell you what it does to a vector that corresponds to one of these yu's, right, to an integer point. Rho of yu is going to be minus the Euler characteristic of y divided by n of u, where n is this number that I was talking about up there. It's the number of times that u covers w. Okay. All right, and now the kind of the magic that comes from some bit of linear algebra and arithmetic and things like that, which seems sort of totally magic to someone, to sort of geometers and topologists, at least certainly to me, is that in this setup you're guaranteed to find one of these guys who maximizes this row, right? Just purely from the arithmetic of this situation. It's all because this cone is cut out by linear equations with integer coefficients. Right? Okay, so I don't have time to explain that, but it's kind of magic. But there is a maximal guy. And then the final thing that you need to do is step 4, which is to show that if a row of yu is maximal, and I've already told you that there will be such a thing, right? Then yu is actually up to sort of homotopy or something, is a surface with boundaries. Okay. So the surfaces magically appear as the maximal points of this function. Okay. And I'm out of time, so I'll stop.
Other questions?
Is there a geometric interpretation for the irrational points of the thing?
The irrational points, I don't know. I'm hoping that Ben will tell me. Where is he? Is he here? Yeah, work in progress, shall we say. Yeah, it's a good question. I mean, they should be sort of something train tracky, but yeah.
So the Caligari paper and several of his other papers, he's also maximizing some quantity to find the surfaces.
He's minimizing. Yeah, no, right. Yeah, so let me try to. I should. Sorry, because I was in a bit of a hurry. I didn't fully acknowledge this. This idea of building a cone is entirely is one that Danny exploited, really beautifully to prove his theorem. This is how he proves his theorem. Here, okay. He looks at a function that's very similar to. Well, okay. There are two differences. Firstly, the cone that he builds only consists of surfaces, right? Not all irreducible things, right? And so he gets going as soon as his cone is non-zero, right? But he needs a hypothesis which guarantees that the cone is non-zero, and that hypothesis comes from homology, all right? In my setting, because I look at all irreducible pairs, I'm guaranteed that my cone is non-zero because we always have the identity map here, because we assume that this guy is irreducible, right? So the identity map always lives here, right? So the cone is always non-zero. But then, right, exactly what's happening is you're maximizing this row, and that takes you up to the surface, to the sort of subcone which consists of surfaces, which is where Danny's machine begins to kick in. Right? So it is very closely related to what Danny does. And it's also closely related to the stable commutator length that Gene was talking about yesterday.
Let's thank Henry and all the speakers.